Hello, everyone, and welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining us here today as we examine linear patterns, proportional relationships, and slope. Now, this is really a tied-together lesson, so if you haven't watched the last couple lessons prior to this one, what we're talking about today may or may not make a whole lot of sense to you, so I would encourage you to make sure that you are familiar with the idea of what makes something linear and what makes something proportional before watching this video. I am going to review those ideas just very quickly. We have said in our previous videos that two relationships are linear if they have a constant rate of change. A constant rate of change. For example, if we look at how meters changes as time passes, we would take our ending meters minus our starting meters. That's going to be the change in meters. And then we're going to take our ending time minus our starting time, and that is going to give us the change in time. And that ratio gives us our constant rate of change. On the other hand, when I say that two relationships are proportional, we're saying that they represent the same ratio. For example, if I just had meters over time, like 5 meters in 1 second, 10 meters in 2 seconds, 15 meters in 3 seconds, and so on and so forth, the ratio of meters and times tells us if these are all the same, that we would have a proportional relationship. I want to connect these two ideas together with a couple different examples. If I have the relationship between the number of students and the number of slices of pizza, let's say one per student has 3 slices of pizza, 2 students have 6 slices of pizza, 3 students have 9 slices of pizza, and 4 students have 12 slices of pizza. And I said to you, is this relationship linear? Well, in order for us to determine that, we would not look at any one of these individual ratios. We would look at how the ratio is changing as time passes. So maybe I want to say, for these first two ratios, I went from 1 student to 2 students and 3 slices of pizza to 6 slices of pizza. So I take my ending students minus my starting students, my ending pizza minus my starting pizza, and I get a rate of change of 1 to 3. That's between this first pair. In order for this to be linear between every pair, I need to always end up with 1/3. So maybe I would say 3 students minus 2 students and 9 slices minus 6 slices of pizza. Well, that's also a ratio of 1/3. And again, if I have 3 students and 4 students and 12 slices of pizza and 9 slices of pizza, I have a ratio of 1/3. Notice that my rate of change is constant. Every time I gain a student, I gain 3 slices of pizza. Therefore, we would say that yes, this is a linear relationship. But is it also proportional? In order for it to be proportional, each of my ratios between students and slices, the 1 to 3, the 2 to 6, which in simplest form is 1 to 3, 3 to 9, which in simplest form is 1 to 3, and 4 to 12, which in simplest form is 1 to 3. In order for this to be proportional, each one of these ratios would have to be the same. They would have to be 1/3. So this is, in fact, proportional. Now, you may have noticed that in this case, our rate of change and each of our ratios is also the same. That does not always occur. However, whenever you have something that is proportional, you will find that it will also be linear and it will have a constant rate of change. Let's look at a couple more examples. I'm going to encourage you to pause the video and try this on your own. I'm going to do these faster each time, but you're going to want to make sure that you understand how I'm computing these by trying it on your own and comparing your answers to mine, rather than just watching me talk our way through it. It's very difficult for you to keep up if you haven't done this on your own instead. Notice I have the ratio blocks used and tower height. I'm going to compare these two things. Is it linear? Well, in order for it to be linear, I need to look at the changes. I go from 1 block to 2 blocks. I go from 5 centimeters to 8 centimeters. So when I set that up, my rate of change would be 3 to 1. If I added one, let's say I did height on top. If I added one block, I gained 3 centimeters. Notice that this time I put the height on top. It really doesn't matter which one we put on top. If I go 11 minus 8 and 3 minus 2, I get 3 to 1. And if I go 14 minus 11, that's a change of 3. And 4 minus 3 is a change of 1 as well. This is, in fact, going to be linear because you have this constant rate of change. Is it proportional? In order for it to be proportional, we're not looking at the change in height and the change in blocks. That little symbol should not be there. That's a typo. I have to go back and get rid of it. I'm just looking at the ratio between height and blocks. So when I look over here at height, I have 5 centimeters for one block. That's 5 to 1. But then the second one is 8 to 2, which is 4 to 1. These do not match. Therefore, this is not going to be proportional. I don't need to check the last ones because if any pair don't match, then I know for sure it's not proportional and I'm done. This is linear, not proportional. Now I'm going to go one step further this time, and I'm actually going to graph these relationships on a coordinate plane. Notice that for one block, I'm going to go up to a tower height of 5 centimeters. Notice I'm at 1, 5. Then I'm going to go over to 2, 8. That's 2 blocks, 8 centimeters. I'm going to go with 3 blocks, 11. And 4 blocks, 14. Notice that because this is linear, when I graph those points, they all fall in a straight line. Not too bad, right? Again, I'm going to recommend that you try this relationship on your own. See if you can figure out if it is linear, then restart the video and see what I have to say. I did my cost on top and my wings on bottom because we said earlier in a previous lesson that, that money tends to be on the top of your ratio. So see if you can figure out if it's linear, restart the video, and then check back in. I'm going to go ahead and do that, assuming that you already have. Notice that when the cost goes from $5 to $10, that's 10 minus 5, my wings increase from 8 to 16 wings. In other words, it cost me $5 extra for 8 extra wings, 5/8 per wing. And I check that with the next pair, 5/8, and I check it with the next pair, also 5/8. This is going to be linear because your rate of change is constant. Is it proportional? Well, again, this delta sign, this change in sign shouldn't be here because I'm just looking at each of these ratios independently. Notice my first ratio was 5 to 8. My second was 10 to 16, which is also 5 to 8. Third is 15 to 24, which is also 5 to 8. And then you've got 20 over 32, which is also 5 to 8. This is both linear and proportional. Linear and proportional. And you can see if I graph those, it's $5 for 8 wings. Notice that I put my dollars up here. It's between 4 and 6. $5 for 8 wings. $10 for 16 wings. $15 for 24 wings. And $20 for 32 wings. You can see as well that this is going to be linear. How about this one? Blue paint and yellow paint. Is it linear, is it proportional, or is it both? Check linear first. Just to be consistent, I went ahead and told you that yellow is on top, but blue is on bottom. It really doesn't matter in this case which one you do, but we all want to do the same thing, and I've already set my graph up in that manner. So pause the video, try that on your own. I'm going to do this one a little bit faster. When we look at the change between 1 gallon or 1 quart of blue to 2 quarts of blue, we went from 7 quarts of yellow to 8. That's a change of 1 to 1. Notice 2 to 3 and 8 to 9 is 1 to 1. And then 9 to 10 and 3 to 4 is also 1 to 1. Notice that your rate of change is constant. Therefore, this will be linear. Is it proportional? I'm going to get rid of these. That's a little bit of a typo there. We're looking at just the ratios this time. 1/7. 2/8 is 1/4. Notice these did not match, so I do not need to check the rest. This will not be proportional. Once again, graphing this. There's your one blue, or 1/4 of blue to 7 yellow, 2 blues to 8 yellow, 3 blues to 9 yellow, 4 blues to 10 yellow, and you can of course see that it's linear. Let's do one more set of these and then we're going to see if we can tie all this together real quick. We're looking at teachers and students. Teachers and students. Is it linear? We're going to put students on top this time, teachers on the bottom. I'm going to recommend that you pause the video, try this on your own. I'm going to keep going, and this time I'm going to do it much, much more quickly. Here we're looking at the change in students compared to the change in teachers. That's 7 to 1. And here we go, 35, 14, 5, and 2. That's 21 to 3, which is 7 to 1. And the last is 70 minus 35 and 10 minus 5, 35 over 5, which is also 7 to 1. Notice these are all the same. This is linear. Is it proportional? Well, let's get rid of those deltas again. Get rid of those deltas. Thank you. We're looking at just the ratio of students to teachers. Notice we have 7 to 1. 14 to 2, which is 7 to 1, 35 to 5, which is 7 to 1, and 70 over 10, which is 7 to 1. This is both linear and proportional because you've got all of these the same. All of these are the same. So when I graph that, 1 teacher to 7 students, 2 teachers to 14 students, 5 teachers for 35 students, and I ran out of room, but we know it would go on to 10 to 70 as well. Notice that is linear. Now let's tie all this together just really quickly. Notice that over here on the left, I have those relationships that were linear but not proportional. And over here I have those graphs that were linear and proportional. These are the same 4 scenarios we just did in the previous slides. I want you to look at these for just a second and see if you can notice anything that might be important. If you need some more time, pause the video so you can think about it a little more. I'm going to go ahead and tell you. Notice that all of these are straight lines. All of them are straight lines. That's because they are all linear. So if it is linear, it is going to have a straight line. But in order for it to be proportional, something else must be true. Can you see what that is? It's something that's true here on the right that is not true over here on the left. Do you see it? It's right here. If the relationship is proportional, it's going to also pass through 0, 0. That's what makes the relationship proportional. Over here on the left, these are linear, but they do not start at 0, 0. Over here on the right, they are linear, but they do start at 0, 0. A couple important things about that. Number one, we can go through and we can identify very quickly what our linear and what our proportional relationships are from graphs without having to do all the trouble we went to on the previous slides. I can look at these graphs and instantly know if they are linear or proportional. The second thing is if something is proportional, I know it's automatically going to be linear. Because to be proportional, it has to meet both sets of conditions. Now that's good news because over here on these previous slides, I'm going to erase all this ink off of those. On these previous slides, it's much easier for me to tell if something's proportional than it is for me to tell if it's linear. To tell if it's proportional, I just need to look at the individual ratios. If it is proportional, it's automatically linear, and I don't need to do all this work. If it's not proportional, it could still be linear, so I would have to go back and check this. Does that all make sense? Let's do this. Here are 4 graphs that we can look at. Remember, we want to draw a conclusion about the graphs of our patterns. If they are linear, they will have a constant rate of change, and therefore they will have a straight line. If they are proportional, they will have both a straight line, both a constant rate of change, and they will go through the origin, which is 0, 0. 2 conditions have to be met. Notice that every proportional relationship is linear, but some linear relationships are not proportional. So let's look at these. If I go through these one at a time, can you tell if this is linear, proportional, neither, or both? Hopefully you can see that this first one, calories over time, is linear but not proportional. It is a straight line, but it does not start at 0, 0. Can you do the second one? Hopefully you can see that it is linear because it's a straight line, but it is also proportional because it passes through 0, 0. This one is both. How about the amount paid in dollars compared to the number of hours? Can you tell that one? Hopefully you can see it as linear but not proportional because it does not pass through 0, 0. And then this last one, hopefully you can look at this very quickly and see that it is not linear. It is also not proportional. Some people get confused and say, well, it goes through 0, 0. Doesn't that make it proportional? No. To be proportional, it has to go through 0, 0 and be a straight line. Not too bad, right? Okay, one last idea I want to throw out at you, and that's this. Suppose you were to graph two pairs of points. What would the slope of the line be that passes through these points? For example, if I have 0, 0 and 3, 7. Your slope is how steep or slanted your line is. In other words, your slope is how quickly it goes up and down. Remember, up and down is the y-axis compared to how it goes side to side. I can actually find the steepness or the slope of this line by comparing the y's to each other, how the y's change, and how the x's change. The same way we did it in our tables earlier in this slide presentation. In order to see the steepness of my line, to see that rate of change, I'm just going to calculate the rate of change between y's and the rate of change for the x's. Remember, it's always the end minus the start. In the case of lines, it really doesn't matter which one you call the end or the start. Most people do the one that's farther to the right as the ending point, but as long as you're consistent, it shouldn't matter. My end minus my start says take the 7 minus the 0, subtract your y's, and then take your 3 minus your 0, subtract your x's, and you get a rate of change of 7/3. In other words, if I have the point 0, 0 on a graph, and I have the point 3, 7 on a graph, the constant rate of change would be a rise of 7 and a run of 3. We'll use this a lot when we begin talking about algebra and linear algebra, how patterns show up on lines. But since we're already talking about rates of change, this seemed like a good place to introduce the idea and at least throw it out there for you. Tell you what, why don't you take a second, pause the video, try and find the slope or rate of change for this second pair of points. Remember, your slope is the change in y compared to the change in x. Or you're going to be subtracting your ending minus your start for your y's, subtract your end minus start for your x's. I'm going to assume that if you wanted to pause the video and do that, you already have. Your y's would be 9 minus 5. Your x's would be 7 minus 2, which gives you 4/5. If you had switched these and had 5 minus 9 and 2 minus 7, you would have got -4 over -5, which is also 4/5. So it doesn't matter which one you do first. Just make sure that if you use your ending as this coordinate, make sure your ending is that coordinate for both x and y. If I wanted to show this to you graphically, there's the 0.25, there's the 0.79. That is a rise of 4 and a run of 5. You have changed 4 spaces along the y-axis and 5 spaces along the x-axis. Here again, I'm going to speed through these last 3 examples. My recommendation to you is that you pause the video between each one, you calculate the slopes on your own, and then you restart the video to see if it matches mine. Certainly you can skim through mine using your fast forward button. You can just look at my answers if you feel pretty confident. I am not going to take the time to graph all of those over here in this empty space, mostly because it's a little bit messy if I get 5 different sets of coordinates on the same graph. But if you want to take a piece of grid paper and try that on your own, it's a good practice or a good a habit to form to verify that what you calculate as your rate of change is indeed what occurs over here on the right. Also keep in mind that we could connect these lines and we could determine whether or not they are proportional as well. So go ahead, give C, D, and E a try on your own. Restart the video, see what you got. I'm going to keep going. My rate of change for C, I got 6/8, which is 3/4. So this graph is going to go up 3 every time it goes to the right 4. For D, I got 10/5, which is 2. This is a rise of 2 every time we get a run of 1. Remember, the whole number 2 is the fraction 2 over 1. And for E, you get -4/6, which is -2/3. Notice that on this one, what happens is every time you go down 2, you're going to go to the right 3. So it might be worth you graphing that one, taking a look at that one on your own. For me, that's all I have for today. Hopefully this has been useful and helpful for you. I know a lot of my students really get confused about how linear and proportional are related, so I created this extra video to kind of clarify that for them just a little bit. Hopefully it has benefited you in the same way. As always, I do appreciate you taking the time to join us here today. Make sure you smash that like button, ring that bell to turn on your notifications, and tell all your friends about all the great things you're learning here at Nunley Math. I do wish you all the very best of luck. Take care of yourselves. Bye-bye.